This lesson is about set differences and symmetric differences of sets. The difference of a set A from B is the set of X in B such that it's not in A. So we write a difference like subtraction. So you can think of difference between numbers, right, as 5 minus 3, which you take away 3 from 5. And the notation for a difference between sets is with the subtraction. So B minus A is you take away the set A from B. Another common notation is B with the backslash A. That's not the notation we're going to use, but it's common enough that I thought I would mention it, just in case you're in a class that's going to use that notation. So, for example, if A is the set 1, 2, 4, and B is the set 1, 2, 3, 5, then B minus A, which is 1, 2, 3, 5 minus 1, 2, 4, is B take away A. So we take away the elements in B that are in A. Sorry, we take away from B the elements that are in A. So the element 1 is in A, so we're going to take away that from B. 2 is in A, so we're going to take away that from B. And then 4 is in A. There is no 4 in B, so there's nothing to take away. So there's no such thing as like negative elements of sets. If the element is in the set B, we take it away. If it isn't, then nothing happens. That leaves us with 3, 5. So whenever we take away all the elements of A from B, we're only left with 3, 5. We can show this in a picture. Let's say that we have sets A and B, where B is the blue circle and A is the red circle. If we take away A from B, the set B minus A is just the set B with A cut out of it, in a sense. So B was the full circle, and we've thrown out all the elements of A, so we've taken away A from B. Another way to represent A minus B with operations that you're already familiar with is B minus A is equal to A complement intersect B. So you could think through why that's the case before you actually compute it. So everything, well, A complement intersect B means everything in B that's not in A, which is the same thing as saying everything in B with A taken away. So it's the stuff in B that isn't in A. And we can show this with logic. So we can do what's called a proof. The element x is in B minus A means x is in B and x is not in A. So that's just logically what it means to say an element x is in B minus A. And to say x is not in A means to say that x is in A complement. So x is not in A is x is in A complement. And that's saying that x is in B and x is in A complement, or in other words, x is in A complement intersect B. So an element is in one of these sets if and only if it's in the other one of these sets. Because it's logically equivalent to say x is in B minus A or x is in A complement intersect B. The symmetric difference is A union B minus A intersect B. It's similar to the exclusive OR. It's all the elements that's in A or B, but not both. And the symbol for symmetric difference is a triangle. So this is A symmetric difference B. So for example, if A is 1, 2, 4 and B is 1, 2, 3, 5, then A symmetric difference B is 1, 2, 3, 5, symmetric difference 1, 2, 4. So we have 1 in both sets, which means we can't include 1. We have 2 in both sets, so we can't include 2. But 3 is only in exactly one set, A, 5 is only in A, and 4 is only in B. So we can include all those elements, and we get 3, 4, 5. So it's all the elements in A or B, or both. If we were to represent this with a picture, we could again show A and B as two circles that represent the sets, and the symmetric difference would just cut out the middle. So the symmetric difference of A and B, we lose this middle part, and it's just the part in A that's not in B unioned with the part in B that isn't in A. So as I mentioned, this symmetric difference, since it's the elements in A or B, but not both, is related to the exclusive OR, and you could write x is an asymmetric difference B as x is an A exclusive OR x is in B. So these two things are connected.